I would like you to stop using design patterns. That does sound ridiculous. I would like you to stop using design patterns like it's 1999. We are past that. It's been a long time. So this is a book. I want to show of hands. Who's read this book? Who has meant to read this book for years and never got around to it? Yeah, more of you. Who thought, sod it, I'm just going to read the head first one by Cathy Sierra instead? Yeah, smart move. It's way better. Not to say it isn't a classic, but that one's just easier to read. But it's a really important book. So it's written by the Gang of Four. And I think over 20 years ago now. I think it was written in 1994, or published in 1994. And it's a book about what we call design patterns. Design patterns, well, this is something Christopher Alexander said. I'll read it out. The elements of this language are entities called patterns. Each pattern describes a problem that occurs over and over again in our environment, and then describes the core of the solution to that problem in such a way that you can use this solution 1,000,000 times over without ever doing it the same way twice. That's taken directly from the book. It's nothing to do with software. Christopher Alexander was an architect, and I don't mean he drew whiteboard pictures. I mean he was an actual architect who designed buildings. And one thing that he observed in his very long career was that people 20 years younger than him were making the same mistakes that he had made 20 years ago. And he wanted to figure out a way to help them surpass him, right? It didn't make any sense for every new generation of architects to do the same thing over and over again. We'd never get anywhere, right? We'd reach, like, you can only go so far that way. He wanted people to be able to learn from stand on the shoulders of giants, learn from the people who come before them, so that they can push the industry and the discipline further and further. So the Gang of Four observed this in architecture and thought, why aren't we doing the same thing in software? And so they took the concept of design patterns, which came out of Christopher Alexander's brain, and they applied it to software. They took a lot of things that they had found themselves using over and over again in different forms, in different languages, in different environments, in different industries, and used them and put them down on paper in such a way that we can use them 1,000,000 times over without ever doing it the same way twice. Now on a slide on functional programming. Who here has used Java 8 in anger? What about in production? All right, some of you. Cool. So I can probably breeze through this, but let's see how it goes. I will ask for questions at the end of this small segment because sometimes it's confusing. So that's a value. It has a name, courses, and the actual value is 3, and it's of type integer. This is also a value. It is of type course, its name is dessert, and it's a chocolate cake. This is also a value. A preparation. Well, this is a preparation object, and it is of type preparation. It has one method, made of, which combines cake mix with some special ingredient. In our case, chocolate above, right? Hope you all ate breakfast. I think this is really interesting. So we can take this code. Actually, before we get onto that. So it's implementing this interface. So the interface is preparation. It has one method, made of, which takes an ingredient and returns a course. And you'll see there that I've tagged it with the annotation functional interface. Now, some of you will already be familiar with this, but bear with me. What that functional interface annotation is doing is guaranteeing that we can do this. So when we have an object that has one method and implements that anonymously, we can actually write it like that in Java 8. That's the lambda syntax. And this is straight translation, right? They are the same thing. They're implemented slightly differently in bytecode. You know, one uses invoke dynamic, and one is actually a class that's built. It's got that little $1. You've probably seen it in your if you unzip your jars. But those are the same thing, right? So we can go one further. I can take that lambda expression extract out the cake mix, because that's the same every time anyway. Let's assume it's immutable and referentially transparent. Get onto that at some point. And we know that the prepare cake object is essentially an invocation of the combined with method on the cake mix, right? So what that means is we can use what's called a method reference. So we take the lambda, we pull that object out, and then it's just simply combined with, like the combined with method on the mix object. So, and you can see that because the inputs and the outputs are the same. Combined with takes an ingredient and returns a course. Preparation takes an ingredient and returns a course. So they have the same type signature. So we can coerce one to the other just by using method references. Everyone's still with me? Let's break that down a little bit further. So if we just look at the inputs and outputs and extract that value out, we can see that the input ingredient and the output course of the combined with method on our cake mix object match exactly the interface preparation. And that's why we can implement it with a method reference that just has the same inputs and outputs. Now that's your 5-minute introduction to functional programming in case you've managed to live under a rock for the last year and a half while Java 8's been out. It's been a year and a half? No, 1 year. Are there any questions at this point before we get on to the meat? Everyone understand lambda expressions and method references? And method reference, all it really is, right, is just a conversion from one thing to another. So we're just converting from that combined with method to a preparation object. Well, that was fast. OK, on to the good stuff. So I want to talk about patterns, because that's what we're here to talk about. The first thing I want to talk about is the abstract factory pattern. Now, this is a creational pattern that's used very, very commonly, especially if you like Spring. I'm not sure if anyone still likes Spring, but in case you like Spring, this is incredibly common, right? And it looks something like this. So we have an interface, I'll call this one bakery, and it makes two things. It makes pastries, it makes cakes. Pastries have toppings, cakes do not. I don't know why cakes don't have toppings, don't ask me. And this is an implementation of our bakery interface. So it accepts a topping, and it returns a pastry, or a Danish pastry, because it's a Danish bakery, or it bakes a cake. And that is Danish for apple cake. I have no idea how to pronounce it. I'd be really interested to find out. So if anyone speaks Danish, please tell me. Say that again? I'm never going to be able to say that, but thank you anyway. More generally, if we go to the chalkboard, the abstract factory pattern can be modeled something like this. So you have the client, which interacts with the abstract factory to produce products. And the client has no idea what the concrete implementations of the factory or the products are, and it doesn't care. So this is a way of abstracting away creation and removing it from the responsibility of the thing that actually is doing the creating. And it doesn't need to know what it's creating. It just needs to know that it fulfills certain contracts. And that's what the abstract factory pattern gives us. And it's a really useful thing. This is a slightly more common thing, usually when we have factories and software, because factories are cheap. In industrial manufacturing, factories are really expensive, but in software, factories are really cheap. So we can make one factory per type of thing. We don't have to have a factory that produces 2 different types of things. This is way more typical, right? So, and our implementation will look something like this. This one doesn't make apple cakes, sorry. But what's really interesting about this is because it has one method, this is de facto a functional interface. So we don't actually need the functional interface annotation to specify its functional interface. That's actually just a compiler thing. It's telling the compiler to give you an error if that's not really a functional interface. But a functional interface is any interface with one, I think, non-default method is the phrase they use now. It used to be single abstract method, and I keep losing track. So one method that's not implemented. You will also maybe have seen in Java 8 that interfaces can now have method implementations using the default keyword. So one non-implemented method. And in this case, we only have one method on the interface, so it's really easy, right? So that is a functional interface, which means we can just replace it with a lambda. OK, there we go, factory. we can go one further. So if you look here, you'll see the inputs here and here are the same, right? So the input to the constructor Danish pastry is actually the same as the input to my lambda expression, and actually the input to my bakery, which means I can do that. So this is a method reference to the static method new, which is on every class, because new is kind of like a static method. Any Ruby programmers will probably agree with me. Any people who haven't written Ruby are probably scratching their heads going, wait, what did you just say? But that's all that new is, right? It's a method, or it's a function on a class that creates instances of that class. It has some magic behind the scenes, and that's okay. That's why it's a keyword. But that's all it really is. So I wanted to explain one more thing at this point. So here, we are assigning this lambda expression to a bakery, and lambdas don't have a type. There's no function. Well, there is a function type in Java, but it's not actually necessary. Lambdas have the type of whatever you assigned them to. And all the compiler will do is make sure the inputs and the outputs match. So you can see there that our bakery interface has one method, bake pastry, and its input is topping and the output is pastry. So as long as the inputs and the outputs of the lambdas match, as long as the type signature is correct, it will convert. Speaking of that function interface, this function interface is in Java 8. It's in the Java util function package. And it is a functional interface, and it has one non-default method called apply. And it's generic, right, as you'd expect a function to be. So it can take a type of any input and return a type of any output, and it's parameterized around those types. It also has a lot more methods, but they are implemented for you. You don't need to implement them. You can override them, but that's a terrible idea. And this is a functional interface. And it's a very, very general thing. So what that means is we may not even need our bakery interface, right? We already managed to remove the implementation. We just replaced it with a lambda. But what if our bakery just implemented the function interface directly? Well, we could turn that into a lambda and turn that into a method reference. By the way, if you use in any IDE, well, any of the big three IDEs at least, I haven't tried any of the smaller ones, you can Alt-Enter or Control-1 your way to this. So you can go from that and just hit Alt-Enter in IntelliJ, and it will just get you to that. So here we have a function from topping to pastry, which called the Danish bakery. We've given it a name, and we've just assigned it that constructor method reference. Constructor reference? I'm not really sure. Let's call it constructor reference. And that's really powerful, right? So we managed to remove the implementation and remove the interface. And yet we still have all the flexibility of the abstract factory pattern because we still have separated creation from use. Now, I'm not suggesting you always remove that interface. Actually, I really liked that bakery interface. It told us what it was. Function from topping to pastry gives you less information. Sometimes it's not always wise to do that. But sometimes it really is boilerplate, right? If you have an abstract factory manager function, maybe you can just use something else, some other built-in interface instead. And you're Java programmers, so I know you have an abstract factory manager function supplier, Spring something manager in there in your code base somewhere. What it means is, even if we want to keep the interface, which we probably do, because it's a useful interface, it gives us a lot of information, the implementation of those interfaces, that's boring, that's boilerplate, it's guff. The products are probably quite interesting, right? I still care about Danish pastries, and I still care about rhubarb tarts. But I don't care where they come from most of the time. Like, factories are a really useful mechanism, but the boilerplate that comes with them, like the 50-line classes and the stuff that's also generated by Spring or Juice or whatever you like to use these days, I can't remember. Those are almost a waste of space, right? They get in the way. They don't really give us any value. The value comes from the interface and the naming and the separation of concerns between creation and use, which is what the abstract factory pattern gives us. All right. The adapter pattern. So you'll probably all be familiar with the adapter pattern, but I don't know which version of the adapter pattern you'll be familiar with. So we're going to go through both of them. So say we have fire. It burns things. And we have oven, which cooks food. Very important. And let's assume we have an implementation of fire called wood fire, and it's implemented somehow. I'm not sure how. Now, this is an example of the class adapter pattern, which looks something like this. So we're going to create a makeshift oven by extending wood fire and implementing the oven interface and implementing the cook method as invoking the burn method on the parent class on the wood fire to create nasty food and then scraping off the burnt bits. That's how I cook. This is the class adapter pattern. I'm not a huge fan because I don't like extending things. We can talk about that later after this session if you fancy it, because I can go on for hours about how the extends keyword is a travesty and we should never use it. But I won't today, at least not right now. So instead, let's talk about a different implementation of the adapter pattern which doesn't have that problem. So we have fire, we have an oven. And this is another makeshift oven. It does the same thing, but in a slightly different way. So it depends on a fire object which is injected through the constructor, and then it uses that fire to burn the food and then scrapes off the burnt bits. You should never come to my house. I'm a terrible cook. So that's the object adapter pattern, called because it depends on objects rather than on class and inheritance. You probably see where I'm going with this. So that's an interface with one method. Its input is food, its output is food. And we use it like this. So we create a makeshift oven, and we use it to cook the pie, and we have a baked pie. I think that's how pies work. This is a much simpler diagram because it's a much simpler pattern. The client interacts with the target, which is the oven. It has no idea that it's really a makeshift oven which wraps a fire, wrapping either through extension or through encapsulation. And that's the beauty of the adapter pattern, right? That's what it gives you. It allows you to present an object as if it were something else. So even though you really have a fire, if something needs an oven, you can get it to it. The adapter pattern does this amazing thing. It kind of bridges worlds. So say you have library A and library B, and you've got your own code in the middle somewhere. You don't have to rely on the fact that the authors of library A knew about library B when they were building their library, and that the authors of library B knew about library A, because they're probably different people anyway, right? What you do have to know is that they provide you decent interfaces. But that's actually like a fairly small ask. As long as you have decent interfaces, you can connect those to yourself, right? You can adapt. You can change one to look like the other and vice versa. And that makes it a lot easier to work with lots and lots of different unrelated things and just connect them all together. It allows you to write glue code, which I think is what's some of the most powerful code in existence. Right? Just code that connects two very useful things together in such a way that you have something that's a little bit more than the sum of its parts. So we've got this interface. Takes food, returns food. It's got one method called cook. And this is the implementation, which you saw earlier. So it's got one method, which means it is a functional interface, which means we can do that. So here's a different implementation of the same thing, right? So our oven is a function that takes in food, burns the food, scrapes off the burn bits, and calls it cooked. And of course, you can collapse that a little bit further. We've got that intermediate variable, which is kind of nice when you're working with methods, to name those things. I think it looks really ugly in that scenario, so I'd probably just stick them together like that, and that's still pretty readable. You've got to be careful with method references. You can go further, right? You do this entirely with method references. It looks like that, which is a terrible, terrible idea. I'll explain it because I think it's really interesting. So we create a function. Because lambdas don't have a type and method references don't have a type, we have to take the method reference to the burn method on fire and assign it to a function so that it knows it's a function. Because I need to use this other method, and then, which composes two functions. So it basically sets the functions up so that we say burn and then scrape off burnt bits. So the input of this new function is the input to burn, and the output is the output to scrape off burnt bits, and it figures out how to push things through. And then oven is just the application of that cook function. So we are just converting the two, right? That's an adapter. And then we cook the pie with the oven. That's way, way harder to read than the thing above, right? And it's kind of a point, like, all my point is that method references, while they seem like a really powerful tool, and they are, they're not always the prettiest things in Java. This is way prettier in Scala. This is really kind of quite removed from your day job. So I want to talk about something that's probably a little closer to home. Everyone know what an executor is? Marvelous. So it's in Java util concurrent. I think it was introduced in Java 5, maybe 6, I can't remember. And it's a very, very simple interface. It just takes a runnable and does something with it. Now, there's a more complex interface which extends executor called executor service, which has like submit and a few other methods that return futures and callables and that kind of thing, except callables. They don't return callables. But that one's very simple. So let's say we have an executor somehow. It's defined in some way using a thread pool or whatever. And we have a bunch of tasks. Now here I'm using the stream concept. Has everyone used streams in Java? I will explain them if not. Can I get a show of hands, people who've used streams? That's like 60%, so I'll explain. A stream is, I guess simply put, it's a view on a collection of data. So, and I don't mean collection in the Java util.collection sense. I mean just a bunch of data, and it's not necessarily ordered, but when you traverse it, it comes out in some order. It's used once. It's very similar to an iterator in that sense. So you use it once, you just stream through it. That's why it's called a stream. You can fly through it, use all the data in it once, and then it is dead. The difference between it and an iterator is it has a bunch of extra methods which are really useful. These are methods like map and filter and all these functional stuff that you've probably seen when you've dabbled in Scala or Groovy, or even played with Java 8. And that's where it's really useful. Now, one of these methods is called for each. And for each is a method that goes through each element in the stream and does something with it. So, but if I want to say for each task in the task, do the executor thing, that doesn't work. Because, well, for each looks like this. It accepts a consumer and then is void. Now, consumer is probably not a thing that you've seen before unless you have played with Java 8, and it looks very similar to this, but with more stuff in it. It's a functional interface. It consumes a thing of type T that's parameterized, and it is void. It doesn't return anything. Now, if you look really closely and squint a little bit, these two interfaces actually look pretty similar. So the top one, we have an executor, which is really just a method that accepts a runnable and returns nothing, is void. Consumer accepts something of type T and returns nothing, it's void. Which means a consumer of runnable has the same kind of type signature, as it were, as the executor. Which means that if I have an executor and a bunch of tasks, I can give it a lambda, because consumer is a functional interface, which for each task executes that task, right? So there's your adapter, right? It's 30 characters? Adapter pattern, done. Right? No more further work, no more objects required, no more classes required. Objects are great, classes are complicated and confusing. So no more classes required. But what I think is really cool is because the input to this consumer and the input to the executor is the same, we can just do that. Okay? Which means that this is an adapter. Right? That's the adapter pattern implemented in 18 characters, I counted. And this is, I think, the power of lambdas in a way that we've never really seen in Java up till now. The ability to just move things around in very, very terse semantics that just, or syntax, terse syntax that just gets to the point. There's no boilerplate. I didn't have to create an executor consumer adapter, or consumer executor adapter, I'm not really sure. Executor consumer adapter. I didn't have to go create a new class with a constructor that took an executor and implemented consumer and was horrible and long. I didn't even have to create an anonymous inner class which did the same thing and was 5 lines long. That's the adapter. So what it means is we can go straight from the target to the adaptee. And the actual implementation of the adapter, well, that's 18 characters. Who cares, right? It's a trivial bit of code. You almost never have to think about it anymore. Conversions are trivial in Java 8, at least for the simple case. And they're even pretty trivial for the non-simple case. Everyone with me? I want to ask if people have any questions at this point. I'm going to take that as a no. Sorry? Go on.
What would you do if the target interface has many methods?
If the target interface has many methods, yeah, you can't do much with that. You still have to say the same thing. My experience has been that in most well-authored libraries, interfaces tend to have 1, maybe 2 methods. There are not that many interfaces in libraries that I've used where, like, they do exist, and there are some really good ones. I mean, WebDriver is a great example of a really cool library with an interface that's 1 billion lines long. But you almost never have to adapt those. When you're adapting things, you're generally just converting small pieces of code from one domain to another.
So we also apply interface segregation principle.
Yeah, exactly. So yeah, that's a great way of putting it. So if you are applying the interface segregation principle well, you will end up with fairly small interfaces, and you can use this nice little trick, right? So, and I want to point out that this is not, only half of what I'm talking about is about lambdas. I was going to get onto this later, but I think it's actually kind of interesting now. I think the important thing is that you're thinking about how to convert between one thing. If you do need to convert between one thing and another, how can we convert with minimum fuss, and where is the value? There's definitely value in the adapter, but there's no value in the class and the curly braces and the @override and the method signature, which is the same as the interface method signature. The value is in the implementation of that method. That's what the lambda gives you. Chain responsibility pattern. So unlike the other two, this is a horrendously complicated pattern. And I don't know how familiar people are with it, but if you've used Java EE, you probably know a little bit. So here's the thing. So let's say we have a bunch of people in a kitchen. So you've got Alice, Bob, Carol, and Dan. They know who the next person to pass their thing to is. And then when we ask Alice to prepare a new pie, she makes the pie, dollop of cream goes on top, cutlery is added, and then it is served to this patron. And we can check that the patron has a pie. That's really weird, and it probably makes no sense. So let me explain using a slightly different example. Totally unreadable. Okay, this is the same thing, but without all the boilerplate. So this is a hit counter. This example was taken almost verbatim off the Java EE's servlets filter chain web page as an example. So do filter is a function that takes 3 things. You have a request, a response, and a chain. And the chain is actually what happens next. So in our hit counter filter, what it does is it gets the counter, which is some singleton somewhere. It increments that counter. It logs it. And then we ask the chain to proceed using the same request and response. So what we've done is elsewhere, we have wired up a chain, usually in XML. And it's the responsibility of every item in the chain to, if necessary, if required, invoke the next thing in the chain. It may not necessarily be with the same objects every time. So here's another example. This is what I've called a switch encoding filter. Never ever do this. This simply changes the encoding of the request, forces it to be UTF-8, which is probably wrong. And then proceeds as normal, but with a modified request. you can also elect not to proceed. For example, an authorization filter might decide to throw an authorization exception if the user is not allowed to access that particular path that they've tried to access, and then, if the exception is not thrown, proceed as normal. So in general, they kind of look like this. So you have a client which talks to the first thing in the chain, and then the first thing in the chain knows about the second thing in the chain, and the second thing in the chain knows about the third thing in the chain. Now, sometimes these things return, in which case something will propagate all the way back to the client. In the filter chain example, response is a mutable object. So these things can and will write to the response object as they proceed. The last thing in the chain will probably actually be your web app, and that will write to the response object, and then the client will just read that once processing is done, and because it's single-threaded, it knows when processing is done, it's when control is returned. So that's kind of chain of responsibility in a nutshell. I want to go back to my toy example because it's way easier to work with. So often we'll wire this stuff up in XML, especially when you're dealing with Java EE, but here I've wired it up in code. So I have these 4 objects, Alice, Bob, Carol, and Dan, and I've just told them who the next person is in the chain. And the forPatron method here is actually a method on server. So, Alice prepares a pie. Oh yeah, so it's a method on the pie. I remember now. So that's passed to the patron. So I have a bunch of problems with this. I actually think chain of responsibility is kind of an anti-pattern. There's a lot of mutation there. You have to know where the start is. There's nothing telling you that Alice is the start of the chain except the fact that we have the code right there. But there's no reason to know that in a large system. Like when you're working with a test case that's 7 lines long, it's easy. When you're working with a code base that's 1 million lines long, it's really hard to know things like that. If we change the order, let me go back to that example. So if I said Alice set next Carol, Carol set next Bob, so if I flip the order there, everything would still compile, and we get a class cast exception at runtime because they're trying to deal with different types of objects. Sometimes you're not even that lucky. Sometimes you don't even get the class cast exception. Sometimes things just happen in the wrong order, which can lead to fun things like security vulnerabilities. And something we saw in the filter chain was that each item in the chain has to do the next thing explicitly. So partially that's duplication, and which means it's really easy to get wrong, but also partially I don't want to have to care about that. It's overhead in my brain. And overhead in your brain is way more costly than overhead anywhere else because you only have so much brain space, far less than a computer does. So the first thing I'd like to do is remove the mutation. And we can do that just by changing the constructors to accept the next thing, right? So Alice is constructed with Bob, Bob is constructed with Carol, and Carol is constructed with Dan. We've had to flip them because, well, you can't construct things with things that are constructed in the future. But apart from that, now at least we've lost the mutation, which is nice now because I can't get the order wrong, because the next step is to start actually typing these things. So I know that Alice will accept an uncooked pie. I know that Bob will only accept a cooked pie. And I know that Carol will only accept a full meal, and Dan will only accept a full meal with cutlery. What that means is I can change my constructor so that instead of just taking an arbitrary kitchen staff member, Alice's constructor, the pie chef constructor, can demand that the next person in the chain is an instance of kitchen staff for cooked pie, which means it has to be Bob. Anyone else would fail to compile. So the next thing I want to do is try and decouple these things a little bit, because I guess my issue with the current situation is that you have to know who the next person in the chain is immediately, which means construction is actually really hard. So it's pretty trivial in our simple example again. But if you had to construct your filter chain, with knowledge of whatever comes next, that would be quite complex and quite brittle and prone to lots of changes every time you wanted to change one thing. So we can do that by adding an extra method. So if we pull out that piece of construction logic into a method called then, it's a method on kitchen stuff, we can say that we construct a PyChef that is independent of anything else, and we say .then Bob, right? Now, the rest of the code is still the same, but one of the things this means is that now we can specify the output type in our type signature as well. Because Alice, or a new PyChef, a PyChef is an implementation of kitchen staff from uncooked pie to cooked pie. A dollop distributor goes from cooked pie to meal, and then cutlery adder goes from meal to a meal with cutlery, and then a server turns a meal with cutlery into a serving. So, but when we compose these, so for example, on the second line, Carol is then composed with Dan, with this, using this then method, the signature changes, right? And that's true because of the implementation of then. And there's only really one possible implementation of this because of the type signature. So given that we have a kitchen staff that goes from I to O, from input to output, the then method has to take the only thing that makes sense, which is a kitchen staff from output to some other output in the future, and return a member of staff from the input to next. And it does this by returning a member of kitchen staff, which takes the input, prepares it, and then invokes prepare on the next person. We can do that with a lambda because kitchen staff is a functional interface, right? It's only got one method. Or it's got two. But this one is default, and that's kind of what I was saying earlier about how default methods don't count because they have an implementation. You don't need to override them. This actually brings interfaces much, much closer to what we've been calling abstract classes. The difference, in case you're wondering, is that abstract classes can still have state. Interfaces cannot. They also can't have private methods or protected or packaged private default access. They have to be. They are all public, and they only have behavior. So the next thing we can do is pull out all those invocations of the then into a new object, or into a new line, which we then assign to a new object. So I'm going to call that staff. It's hard to see that purple, but this says staff, which is also what we use down here, and this is the first time the rest of the code has changed, except when we made it immutable earlier. What that means is we can construct Alice, Bob, Carol, and Dan independently. They are independent objects. They have inputs and they have outputs. Notice that we're no longer invoking the next thing directly, but instead returning an object, which then can be composed with the next thing. And then we compose them all into an object called staff. Now it's really obvious where the start of this chain is, right? It's staff. That's the only thing that composes all the things together. So we've separated out the actual construction of the chain from the construction of all the objects in the chain, which is something we merge back together in order to get some immutability. Now, kind of the last thing I want to show you here is that the then method that we wrote is incredibly similar to the and then method that we saw earlier on function. So a function is an interface with two generic parameters, t and r, and it takes a t and returns an r. But it also has a default method called and then, which takes another function from r to v, where v is a new type parameter. And it applies self to t, takes the output of that, and applies the second function, which goes from r to v, and it returns. That constructs a new function from t to v, which I think is pretty cool. What that means is we can replace this kitchen staff object with a function. It's the same thing, right? It is a thing from I to O, or t to r, and it's got an and then method or a then method or whatever you want to call it, which composes functions. This is just function composition at this point, right? And that's in my opinion, the only thing that the chain of responsibility pattern does is just function composition, right? With a bit of mutation thrown in. But as soon as you remove the mutation, you just have pure functions. You have functions with inputs and outputs, and you can just stick them together. Now we can go one step further, and I just like this because it's interesting, not because it's relevant, which is to just replace those objects, PyChef, etc., with the method references that they are wrapping. The interface is interesting. The implementation's not so much. So we can just construct them as necessary. So in this pattern, unlike the others, we totally rejigged it. So now A, B, and C have no idea about each other, which makes sense to me, right? That's previously it was a violation of the single responsibility principle. You shouldn't have to do a thing and then invoke the next thing. You should either have to do a thing or be responsible for invoking things in order, which is what we have now, right? That's our function composition. So we've created a composite. This is an implementation of the composite pattern, right? Composites don't necessarily have to mean traversing over a list. They can also mean function composition. So we have 3 handlers, which are all implementations of our composite, and we also have a 4th implementation, or actually a 5th in our case, which is the composition of all of those 4 things. And the client just knows about that composite. All right. So I have a point. So we first talk about bakeries and the abstract factory pattern. I'm getting really hungry. We talked about how even though the interface, which describes actually like what we're trying to achieve, right? The interface is like it defines our inputs and our outputs. It tells us what we want. The implementation, well, it's an implementation detail. Who cares, right? The domain is what's important. So the actual implementation of how abstract factory works was kind of irrelevant, and we saw that again and again in the other patterns too. We don't need to create so much ceremony over things that are implementation details. We should be reserving that ceremony for the things that actually matter, the things in our domain. So the implementations of the products, so our Danish pastry, which is the implementation of pastry, usually that stuff matters, right? The nouns in your code, like they're there for a reason. They're really important. The verbs too. The factories, not so much. Who cares about factories, right? They're just there for decoupling purposes. Like I said, the interface may or may not be important, but the implementation almost never is. We then talked about ovens. No, adapters. And this, I think, is just really interesting because adaptation is something we do all the time in code. And again, it requires so much ceremony, so much work. And just by treating our code as if it were very, very small building blocks, and now we finally have some syntax that allows us to treat it like it's very, very small building blocks instead of making everything a class, we can do that, and we can just kind of break it down. And then we had this behavioral pattern to do with making pies, the chain of responsibility pattern, which I feel like is an anti-pattern. Like that's how I kind of see it. I know it's in the book, and I know they're very clever people, but it just doesn't sit right with me. That wants to, like, basically we've reinvented Lisp, right? So we've gone all the way back to 1958, where Lisp was a thing, which people actually use. Closures doesn't really feel like a Lisp, to be honest, but we've gone back to, well, our object that's really just a function. It's the thing that takes a thing and returns another thing. And then we stick them together, right? And this is how coding is supposed to work. We're supposed to be able to reuse components. And how can we reuse things when they do 17 things, or even 2 things, right? How can we reuse something that does 2 things very easily? Now, if something just takes an input, returns an output, and that is the end of the story, it has no side effects, it has no mutations, it doesn't do a second thing, then it's trivial to reuse. So I kind of want you to stop using design patterns like it's 1999. Really like you to start using them like it's 1958. It's funny, right? I don't know if anyone's read the book Gödel Shabak by Douglas Hofstadter. He talks about these strange loops. And Martin Odersky, I've heard third hand, once said that object-oriented programming is not a paradigm. There are three paradigms: structural, functional, and logical. And object-oriented programming is something totally different. It sits on top of any one of those. We can write functional object-oriented code, right? Which is this really, really strange loop. So Hofstadter talked about how often the way we get a lot of power out of things is by breaking layers, by creating loops that go up and down. And I think that's a really, really powerful concept, and we should remember that just because we're writing OO code doesn't mean it also has to be structural. It can be functional. It can probably be logical, although I've never seen that. I'd love to see it if anyone has an example. So those pictures I use by these lovely people are Flickr. I work for Codurance, where we just tear code apart like this all the time. And if you want, there's basically a transcript of this talk on that website. Thank you very much.